So this is going to be our first video on the fifth module of this course, and we are going to study the random variate generation procedure because we have learned how to generate a randomness which conform to the uniformity and independence properties between 0 and 1 unit interval. And now it is time to practice the generation of other random quantities from the real world practices. So this is dealt by the random variate generation topic, and the outline is as follows. First, we are going to define the concept of random variate. Now you may say actually it is a random variable. So what is a random variate? Actually, the random variate is a practical realization of a random variable. So random variable is something that is in the theory, something that we use as a model, but when a random variable is realized, when you observe that a random variable is equal to a certain quantity, that value becomes a random variate. So a practical realization of a random variable is called a random variate. And then we are going to learn about the most famous random variate generation technique, which is called the inverse transform technique, as a part of the first section. Then we are just going to use the inverse transform technique to generate random variates from the most practical distributions that we know from the probability theory course. And actually, these distributions are also very useful in practical discrete event simulation models. So we will learn how to implement the inverse transform technique to generate random variates from other random distributions such as continuous uniform random variates, exponential distribution, triangular distribution, or normal distribution. And then we are going to learn about the same technique, inverse transform technique, to generate random variates from empirical distributions. So not every time we will have a certain probability model. Sometimes we are just going to have only the data itself from a real system, and we will not be able to fit any probability model to there. Then this means we need to generate random variates from the data itself, and this is called generating random variates from empirical distributions. And we will learn how to generate discrete random variables for the first time. Now, if you realize all four examples in the second section are continuous distribution. So this is the first time that we are going to learn how we can use inverse transform technique to generate random variates from discrete empirical distributions. And then we are going to learn about the inverse transform technique, again, to generate other type of discrete random variates, such as discrete uniform distribution and geometric distribution. Actually, there is not a simple way of generating random variates from Poisson distribution. Therefore, we are going to assume that generating random variates from Poisson distribution is the same way as generation of discrete random variates from empirical distribution. And finally, we are going to finalize this chapter by learning another random variate generation technique, because inverse transform technique is just one of the ways. It is maybe the most important and most famous way of a generation of random variates, but there are other techniques as well, and they have their own advantages and disadvantages. Another technique is called the acceptance rejection technique, and we are going to learn about this technique in its simplest form, and we are just going to mention about the other generation techniques in name, but we are not going to learn how they work. And this is just going to be the outline of the fifth module of our class. Okay. So what we have learned so far, as we have said, we have learned how to generate a sequence of random numbers, and we have said that they are pseudo-random numbers, and they are distributed between 0 and 1. They were taking rational values between 0 and 1, and they possess these two important properties, uniformity and independence. So according to the uniformity property, what we know is a random number in a random number sequence follows the properties of a random variable, which is supposed to be distributed uniformly between 0 and 1 and continuously, right? So all of these random numbers, they follow the uniform distribution between 0 and 1. Now, actually, in a discrete event system simulation, what we want to generate is not just in the form of a standard uniform distribution, right? For example, in order to generate the artificial history of the system, we would like to generate the activity duration times and in what forms of distribution they can have. So we have uniform distribution, exponential distribution, triangular distribution, or normal distribution. So the activity duration times can be adapting any of these probabilistic models. Another probabilistic value is the attributes of entities, right? And they usually follow a discrete random variable. For example, let's just say we have a unisex hairdresser shop and 60% of the customers are females and 40% of the customers are male. Actually, the gender attribute is a discrete random variable, and it is actually a Bernoulli random variable. I mean, there are two classes here. And according to the probability masses of 0.60 and 0.40, we need to determine for every arriving customer a gender, right? So first they will arrive, then we are going to observe their genders, from which gender the next customer is. So another random occurrence is the outcomes of the random experiments, such as demand. Now, if you are just going to simulate a manufacturing system or a marketing system, the demand is a variable that is almost unavoidable. You need to definitely put the demand in your model if you want to simulate such a system. And the demand is usually a random factor, right? So we need to be able to generate the artificial history of the demand as well if you want to generate the artificial history of such systems. Now, you see, what we want to generate is not just the random numbers from standard uniform distribution. We want to generate random variates from other type of distributions. So the question here is this: how can we generate random variates that follow other distributions than the standard uniform distribution? So a random variate is called a particular realization of a random variable. When you generate statistical data that follows a certain distribution, then that practical data with quantified values are random variates, basically. Now, the suggested method is this: since we have a randomness in the random number sequences that we have generated, and by the way, please notice at this point, I will use the term of random number for standard uniform distribution only. The other randomnesses are called random variates. So random variates are the ones that follow other distributions. Random numbers are the ones that only follow a standard and continuous uniform distribution. So we are going to use the pseudo-random number sequences and we are going to transform them to random variates such as x1, x2, and x3. So we have n random numbers. All of them will be converted into a random variate which follows a specific distribution, and that specific distribution is defined by its cumulative distribution function. So this capital F here means the cumulative distribution function of that specific distribution, and this sign here indicates that these random variates are following that distribution. So basically, as a raw material, we will have the random numbers generated by a random numbers generation algorithm, and we will also have a cumulative distribution function to indicate a specific distribution. And with these random number sequences and with this cumulative distribution function, we are going to generate random variates following that distribution. Now, here in this chapter, our objective is to learn how to generate random variates from a conceptual distribution, a known and a famous distribution, such as normal distribution or exponential distribution, or empirical continuous and discrete probability distributions, which means they may not be actually known, but they may be defined through their probability density functions or probability mass functions, or they can be generated through data itself. So we are going to learn all of them in this chapter. And here, let us remind ourselves about the continuous uniform distribution between 0 and 1. So remember, we have said that random variable R. So here we are stating that R is a random variable. It's not a random number. We are speaking because in theoretical terms. the random variable R is a continuous and uniform random variable, or it is distributed continuously and uniformly if it has the probability density function that is equal to 1 between 0, 1 interval, and elsewhere the PDF is 0. So this lowercase f sub r indicates the PDF of a standard uniform random variable. And of course, if it has this PDF, it will have this cumulative distribution function. So this means the CDF of a continuous uniform random variable between 0 and 1 is equal to an identity function between 0 and 1. So for all values that are less than 0, the CDF is equal to 0. Then it increases linearly in the form of an identity function. And when it reaches to 1, the whole domain of this random variable ends. And after 1, it remains at 1 and stays constant at there until infinity. So the CDF is in this form and the PDF is in this form for a standard uniform random variable. And what we expect from a random number sequence, as we have said, they must conform to the independence property and uniformity property. So how do we check if they conform to the uniformity property? The simplest way is to draw a histogram. So if you have a sufficiently long sequence of random numbers, you can divide the unit interval into equidistant subintervals, and you count observed frequencies in each subinterval, and this histogram, it behaves as constant if the observed frequencies are approximately close to each other in each subinterval. Then we say that the sequence conforms to the uniformity property. And as we have said, they must possess the independence property as well.